should meet him. And yeah, I will continue this theme, but from a bit different point of view. I will also make a kind of link between certain kind of categories and a certain kind of lattices, but more from a logical point of view, specifically categorical logic and quantum logic. And I come from a categorical logic point of view, so if I use too much category speak, so please stop me and have me explain. So I'll give you a quick introduction on what quantum logic is about, which I'll did a bit of this. So you could roughly say that logic is the study of predicates on a state space. Classically, you would have a set of states, and a subset would be some proposition, saying the system is in this state. And Berkhoff and von Neumann in 1936, they said you can do the same thing for quantum logic, except now your state space is in over space, and you need to not look at subsets, but closed subspaces. Those are the things you can measure. So it behaves a bit like classical logic, but not completely. It has a kind of negation, and the double negation is the same thing again. But especially the distributivity goes on. A very easy example is if Radboud is a two-dimensional Hilbert space, I have a T closed subspace, subsets. We call X, Y, and Z. So the left-hand side of a distributive law here, X, Y, or Z. Y or Z spans the whole thing. So this is just the whole board, and the intersection with X itself is X. But the right-hand side is the intersection of X and Y is just the origin here, which should be 1 point, and this is also the origin, so this is 0, and this is definitely not the same again, obviously. So you're stuck with what's called orthomodular lattices. This is a special case of distributivity. And you can study this as a kind of lattice of the logical propositions, but it has some Achilles heels. For example, there's not a good implication. By a good implication, I mean if I can derive conclusion Z from the hypothesis X and Y, that should be the same as deriving Y implies Z from hypothesis X. It's almost by definition what implication means. Now, in general, in orthomodular lattice, there's no such thing. The best you can do is what's called Sasaki. It's defined like that, and it has this distribution property, but only for compatible X and Y. Compatible in the sense that you can measure them on the same basis. Yeah, so this is the structures that we will see pop out later from a categorical point of view. These are the categories I want to look at. And I want to emphasize, first of all, this is a very, very general kind of category. I'll not try to motivate it physically, but I will love to tell some physicists to me why this is a good thing to do. So I want to have a dagger. You've seen this before. It's just a way to flip the morphisms. Furthermore, I want to have a zero object. So that's an object. Maps into it are unique. There's just one map from an object X to an object 0. And because of the dagger, which makes everything self-dual, it also means morphisms going out of it are unique. And in examples, this is really, it behaves like the zero-dimensional space. And then the last thing I want is to have kernels. And you all know what kernels are in a linear algebra setting. And I'm going to dress it up a bit more categorically for those who haven't seen it before. It's a special kind of dagger limits, as Jamie was telling you about, a very easy kind. Namely of this diagram, 2 objects and 2 arrows. One is the 0 arrow, so it goes from the unique one to 0 and then the unique one to Y again. And the kernel of it is a certain morphism, such that if I do the kernel and then F, it's the same as doing kernel and then 0, which is 0. And moreover, it's the biggest such thing. That means if there's a different one, that's such that the composition with F is 0, then it should embed into the kernel. That's what I will use as kernels. And we'll see this is a very large class of things. I'll give you a wide range of examples. They don't require anything about dimension or byproducts or tensor products or whatever. And it's really the dagger which does all the work. The kernels are a bit, I would say, the least strengthened requirement. So what I will study about these things is the subobjects. So remember, logic was about studying subspaces of space, if you like. Now we're in a category, so we should study subobjects of objects. So what is this? We don't have anything like subsets to speak of, we just have injections usually, monomorphisms. But an injection is not the same thing exactly as a subset. You need to have equivalence classes of these things. So that's what I will call a subobject. And these obviously come with a partial order. If I have some subobject represented by an injection here, and another one, then I can say that the subset this thing represents is smaller than this one if it factors via the bigger one. Now, Berker van Neumann, they said, you should only look at the closed subspaces, because this is the things we can measure, not all subspaces. So we'll factor out some of them, we'll throw away some of the subobjects, and just look at the kernel subobjects, as I'll call them. And this is the special subobjects that come from kernels. In the category of Hilbert spaces, for example, a kernel is the same thing as a closed subspace. The thing to note here is that though I draw this diagram with one arrow here, this is really only defined up to isomorphism. If I have a different arrow which is isomorphic to this one, then that's also a kernel, but it will still represent the same subobject. So these are the things I'm looking at. And now I'm going to do a very unpedagogical thing. I'll launch straight into a proof that this is actually what Berker van Neumann were looking at, these ortholattices, and only then will I show you examples. And the idea is that you see that this structure gives very fast the orthomodular structure in a very canonical way. So the first thing, the lemma here, it says that you can take pullbacks of kernels, that means kind of intersections. And if you compute what they are, the pullback of a kernel and an arbitrary map, this thing here you can explicitly give. It's given by the kernel of the co-kernel of k followed by f. I should have mentioned before that because I have this dagger around the category self-dual, so it means if I have a certain kind of limit, I also have the same kind of co-limit. Specifically, if I have kernels, I can make co-kernels by just daggering the functor first, taking the kernel, and then daggering the result again. So taking the kernel of the co-kernel is sort of a closure operation. And this formula here gives you a pullback. This immediately shows that there's a conjunction on our post set of kernel subobjects. Because if I take two kernels here, then the intersection is just, the conjunction is just the pullback of the two, because it embeds in both of them, and it's the biggest such thing. So it's the least upper bound of the two, least lower bound, greatest lower bound, sorry. And it obviously has the greatest element in the lead identity. But you also get for free an orthocomplementation. At first, it's just a complementation. I can take a kernel K, I can dagger it, so it's something out of an object again, and then I can take its kernel. And this thing will play the role of the perp operation. And you can prove that if I do this twice to a kernel, then it's the same thing again. I come back to the same kernel. So we had a semi-lattice with a meet, and now I have an ortho poset. And if I combine them, I get an actual full lattice by using this kind of De Morgan law. I can define a join of the two by using the meet and perping them first, then doing the meet and perping again. So we have a full lattice pretty quickly already. Then the last thing to check is that it's actually orthomodular. I will use this compact formulation that John had on the board. So first thing to note is that this is a subobject. And the point of this proof is not to bore you, it's just to show you that it's, what is it, 5 lines, and there you have it. My point is to show you that the structure I started with is, you could say, is canonical. And so first thing, this square here is obviously a pullback. If I assume that k is less than L, KL, that means k should factor via L. So this means k goes via L. And what I have to prove is that this square is also a pullback. Because if I can do that, then the lower line here, this is what we needed to prove. Just fill out k factored via L, this left conjunction of K, per, and L is this thing, this morphism. So I fill that out also. Then I know that L is a left adjoint, so it preserves the joints. And you come here. And then this is easy to see that that's just the identity. It comes from the orthocomplementation, and you're done. So what you need to show that this is actually a pullback is I used this lemma of a few slides back. I could actually give an explicit form for this thing, and I'll show that phi per is actually of this explicit form. So what we need to compute is that this is equal to that. And well, this is just 5 lines. You fill out what it means. This is this explicit form. Then I fill out the definition of per here. I use that the co-kernel of a kernel of a co-kernel is a kernel again. Yeah. Then we use the assumption that K is less than L. And that's the definition again. Then you're there. So that's quite quickly. And I see you're all bored, so I can give you some examples now. First, some obvious examples, the category of sets and relations, for example. Objects are just sets. Morphisms are relations between them, and the dagger is giving the converse of a relation. If you draw a relation like such, you think the span between x and y, so R is just really a subset of x times y, so it has a projection to x and a projection to y. Then the dagger is just flipping this thing around the span. The zero object is the empty set. This thing has kernels, meaning the following. The kernel I take to be the set of all x's which are not connected to any y. And I include that just into x. Dagger monos I didn't tell you about. This is what I call, let me go back to it. I want all my kernels to have this form, to be isometries if you like. So what I call a dagger mono is a morphism M, such that if I do M and then go back with a dagger, nothing should have happened. In this category of sets and relations, the dagger monos are precisely things of this form, where this first projection is a surjection, and the second one is an injection. And this is obviously of that form, because an identity is a surjection. But this is a category that John also showed. It has byproducts, for example. So let's cut out some stuff to show that you don't really need the byproducts and all the rest of the stuff. I'll look at partial injections. It's a special kind of relations, if you like. You can still draw them like this. But now I want both of these legs to be injections here. The dagger is still flipping. The zero object is the same. The kernels are the same. The dagger monos now, because this first needed to be a surjection, and I require all morphisms to be the first leg an injection, so it can only be a bijection. So you see here already that kernels and dagger monos are the same in this category, but in the previous one, there's a difference between the bottom two things. So this is really, they categorically differ, these two categories, but both are instances of my general scheme. Other categories of Hilbert spaces, which you all know. Notice I know nothing about dimension here. It works for any Hilbert space at all. Because, whether each representation theorem adjoint exists, it has a zero object, it has kernels, obviously. And one is by definition the dagger monos are the isometries. So this is also an instance of my scheme. And it's funny to note that the L2 functor, which kind of gives the free Hilbert space, preserves all this structure I'm looking at. Also, this category of Hilbert spaces has byproducts, and you can throw them out, as you were just discussing after the previous talk. I'm not sure if you can go to completely positive maps. I haven't checked. You can identify two morphisms when they just differ by a scalar phase. Then you call that's the same thing as looking at the unit circles of Hilbert spaces and the functions which descend to that. So I call this projective Hilbert spaces category. And all the structure of Hilbert spaces that we're looking at descends together. The dagger is the same, the zero object is the same, the kernels are the same, and the dagger monos are the same. And this functor which takes a Hilbert space and makes it projective still preserves all this structure again. And final example I want to show you is a bit of a funny one. It's into a category, but not in the usual way. Usually you would take a post set and then make a category by having one morphism, one x is smaller than y. But here it's a bit different. Objects are still taking the elements of the lattice. But now I say morphism for x and y is an element which is smaller than both of them. I haven't seen this before, but it works here. It has the composition, just the heat as identities, so it's a proper category. I can put a trivial dagger on it. It has a zero object and it has kernels, given by the application of the Boolean algebra. And dagger monos are things of this form. Okay, so let's look a bit at the structure of these kinds of categories, because now things will start popping up. First of all, I'm going to show that every morphism can be factored in a certain way, as a kernel followed by something else, and something else is a bit more general than FE. I define a morphism E to be 0 FE if this condition holds here. If I follow it by F, if the composition with F is 0, then the morphism F itself should be 0. You can characterize it precisely by saying that its co-kernel is 0. And now you can immediately see that these examples I gave you really behave categorically differently, because now I look at all these classes of different morphisms I've been looking at. That kernel, which was by definition, I required this to be dagger mono. Dagger mono is again a special case of mono, and this was still more general than just classes. But in sets and relations, there are zero monos which are not monos, and there are monos which are not dagger monos, and there are dagger monos which are not kernels. But in other categories, for example, in sets and partial injection, this is precisely the same notion. And there are things in between here. For example, room space, the kernel is the same as a dagger mono. So they are really different things. Now this is the factorization I promised you. Any morphism F, I can write it as kernel I followed by 0 FEE. This is even the factorial way. You can do it in two ways. Then there's a morphism in between saying that I and I prime are almost the same thing, E prime. So now I can write every morphism as a 0 FE and then a kernel, and I can use my dagger to factorize this thing again in a co-kernel and then a 0 mono. So I guess you can get this kind of structure for any morphism. First you do what's called a co-image, dagger FE. At the end you do a kernel, a dagger mono, and this is where all the action happens in the middle. This is the outer two things are really just two key things. And once you have the factorization thing, you get an existential quantifier for free. This is what categorical logic is very good at. It's a kind of unified setting for any logic that deserves a name. And the prescription is the existential quantifier, this thing, is a functor that should be left to join two pullbacks. And this thing exists in our setting. So if F is a morphism for x and y, I can take the pullback with any subset, subobject of y, and I get the subset of x. And this factorization gives me the other way, because I have, where is it? A is now a kernel subobject of x. I can follow it by F, so I end up in y. If I factorize it, the image of it is a kernel subobject of y. And this turns out to be really the left adjoint, so that works. But this is very different from what quantum logic people have tried to do before. And I'd almost say it's more canonical, but time will tell. And we'll see now that it's also a bit strange from a categorical logic point of view, because this existential quantifier, its goal exists, but it really doesn't behave like you would expect in a classical case. And this, I think, will be explained in the next talk a bit as well. In a sense, it behaves more time-like on the music. So once we have this left adjoint here, I can use it to give a special case, namely the Sasaki loop that we saw before, the simplification. If I take any kernel subobject, I can make this the projection, if you like, onto it, orthogonal projection. And I use this thing as a special case for its morphism on the previous slide. So here's my thing. I pull back some object, and this is precisely the society. So this is really just a special case of this categorical adjunction. And on the other side, you can also get an and-then operation, which is kind of first like this measurement and then that. Quite like this usually. And that's also a special case if the exists for something. And then by construction you have this what's called the society adjunction. So this is kind of a weak form of the mating implication that we saw on the first slide. But this really doesn't behave like a conjunction. This is known by quantum people, quantum logic people as well. This is not really different in general. So first we'll do experiment A and then B, there could be side effects and we cancel the two. And you can even characterize precisely when the logic of this thing behaves classically by the following. This is also a very short and canonical definition, I'd say. For any two kernels, if their conjunction, their intersection is empty, then they should be orthogonal. That's what I call the category Boolean. This example category I showed you when I took the Boolean algebra, made it into a dagger kernel category. This is an example of a Boolean category in this sense. And you can prove that this implication here, the other half comes for free. So that means the category is Boolean if disjointness is the same as orthogonality. And you can even go on to show that the category is Boolean if and only if all of the subspace lattices, subobject lattices, are Boolean algebras. So that's precisely what you would want to see for a classical kind of behavior. This slide I will skip. And I will tell you some other fun things. So much of the power of categorical logic comes from having subobject classifiers. People who know some topos theory might know about this. So in general, this is an object that, well, the name says it actually, it classifies subobjects. It means if I have some subobject M, if you have a subset M of X, that's the same thing as giving a characteristic function. It just says, it gives you 0 if an element is not in M, and it gives you 1 if an element is. And to complete the diagram, you can do this. So this object here really plays a special role in sets and functions in the category of the topos. And this property here is called being a subobject classifier. You can formulate it a bit differently because this diagram I draw here is natural in M. If I change this for a different M, things will still work. I can formulate it as follows. There's a bijection between all the subobjects of a set and the function from the set to 0, 1. This is what I draw there. And it's natural in the sense that if I pull it back and I recompose it with any morphism, this bijection still works. Now in these dagger kernel categories there's something similar going on, but it's a bit different. Because we have this dagger around, so the category is self-dual. And this plays up in a sense. For example, in the category of sets and relations, if you calculate what the subobjects of a set are, that's just the power set, really the classical case. And it turns that this bijection is also natural in a way. You can write the power set of X as relations from a one-element set to the set itself, this thing. And there's a similar kind of naturality going on as for subobject classifiers. Except now I don't use pullback, but it's left adjoint. And I don't use pre-composition, but I use post-composition. So we temporarily term this being an op classifier, and for lack of a better term. And this phenomenon pops up in other examples as well. For example, this example where I took a Boolean algebra, made it into a category. There's also this bijection going on, namely if you calculate what the kernel subobjects of a given element are, it's really just the principal downsets, everything that's below it. So there's obviously something going on here that we'd like to understand from a categorical logic point of view. I think I should end there. Thank you.
actually, as John was asking himself, if you have a monoidal structure, how would it interact with this construction?
That's a very good question, because for example, it's not clear a priori, right? In sets and Hilbert spaces and continuous linear maps, for example, the kernel of a tensor product has nothing to do in general with the tensor product of the kernels. One is embedded in the other, but that's it. There's really counterexamples. So I don't know. This doesn't help in that respect. You could try to hunt for, as John is doing, kind of tensor product of these case lattices, if you like that. So what you would really like, the holy grail, would be something like this. So this is the tensor product you're given in the category. And this is the thing you're looking for. That's what you're asking, right? Like that. I haven't found it yet. But neither has anyone else.
Does pullback also have a right adjoint?
No, not in general. Because if it has a right adjoint,
can you identify the expansible maps? Or sometimes it has.
I'm not sure about that. Usually, Joachim is saying you have a left adjoint pullback, and sometimes there's also a right adjoint. And usually, this is defined as this. At least in the books I know of. And to show that it's a right adjoint, you use this equation, but also that pullback preserves this negation, which is not true in our case. So you'll need at least to find a different thing. In some cases, you can actually prove that this thing cannot exist at all, because if you have such a thing, then all the subobject lattices must have a heighting negation, heighting implication. And we've seen this example there is all distributive, so it can't be heighting at all.